So, we will continue the discussion on unbounded operators and introduce some more terminology. So, this is one graph norm of A and then graph itself. Okay. So, this is just graph of A. So, this is a subset of, so I denote it by G of A. So, this is set of all pair of points A x as x varies in dA. So, this is a subset of the Cartesian product x cross x. Okay. And since A is linear implies GA is a subspace of x cross x. Okay. So, the third concept, again these are definitions. So, A is closed. Okay. So, this comes very close to the continuity or boundedness of the operator. A is closed if GA is a closed subspace of x cross x. Okay. So, this is the definition. Equivalently, so you can write it using sequences. A is closed if the two conditions, namely this xn in dA, xn converges to x, this is in the norm x, and Axn converges to y. Okay. So, these two conditions imply x is in dA and Ax equal to y. So, when A is continuous, xn converges to x, that itself implies Axn converges to Ax. So, since A is not continuous, so this extra assumption is required. Okay. So, xn converges and Axn converges, and then we have this limit. Okay. That is equivalent to saying that the graph itself is a closed subspace. Okay. So, here is a small proposition. So, that is very easy to verify. So, A is closed if and only if this dA with graph norm. Okay. So, sometimes we also write this as dA. So, in this dA you introduce this graph norm is a Banach space. So, you have several equivalents of this property of a closed operator. Okay. So, very easy to verify. So, one more definition, A is densely defined if dA is dense in X. So, the generator of a semi group, it turns out that it is a densely defined closure operator. Okay. So, that will come little later. So, this densely defined closure operators are the main objects of our study. Okay. So, one remark about equality of two linear operators and extension restriction will do that. Okay. So, an example again, a simple example. So, for example, just you take x equal to L to R, okay, and I want to define AF equal to F prime, F in X. So, we have now many choices for domains of this definition. Okay. So, one domain we take all the classical things. Okay. So, F C1 for example. Of course, C1 function need not be integrable. So, again you put compact support. Okay. So, this on this domain we can define that. So, and other possibility, so you take F in X and then you take F prime. So, this certainly exists in the sense of distributions and you demand that is also in X. So, on both these D1 and D2 we can define this differential operator, namely AF equal to F prime, but technically and even qualitatively these two are two different operators. So, if you define A1 F equal to F prime for F in D1, let me put Di. So, A1 is not the same as A2. Okay. So, that brings us to, so when the equality holds and other one more concept. Okay. Suppose so A and B are linear operators in X. So, with corresponding dA and dB. We say A is a restriction of B, equivalently B is an extension of A. If dA is a subspace of dB and this is important, Ax equal to Bx for all x in D. Okay. So, in that sense So, therefore, no, thus A equal to B if and only if but notation, okay, just notation we write A is restriction of, okay. So, these are not sets, okay. So, these are operators, but still that notation is used. A is a restriction of B and B is a restriction of A, okay. So, the domains have to be coincide and their values also should be. So, even if domains are different, but the expressions are different, then they are not same operators, right. Okay. Okay. So, one more important concept we do need. So, this is namely of the spectrum and resolvent of A. Okay. Suppose lambda is a complex number and you consider so many concepts. So, just okay. With that thing. So, this suppose I have two linear operators A and B. Okay. So, this A plus B is defined. So, you have to be a bit careful while dealing with unbounded operators, because they are not defined on the whole space. Okay. So, the domain of this A plus B is dA intersection D, and a usual definition. So, okay, just AX A plus B X is AX plus BX for X in dA plus B. And similarly, this composition or multiplication. So, this domain of AB, okay. So, you have to do many examples to get familiarity with these new objects. So, first of all, in order to define this ABX, so X has to be in domain of B, and that is not sufficient. So, then this BX has to be domain of A. Okay. So, then we define this AB of X for such X in DAB, A of BX. Just to see that these expressions make sense. Okay. Finally, that is the thing. Okay. Just so consider this. So, the identity. So, there is no problem in defining this lambda I minus A, and that is again domain. If you consider here, I is defined on the entire space. So, this lambda I minus A is defined on dA. Okay. So, assume that one. if lambda belongs to C is such that the operator lambda I minus A, so this is from dA into x is 1 on to. So, lambda I minus A inverse as a mapping certainly defined, okay, and so this lambda I minus A inverse is defined as a linear operator, but you demand that is in Px. Okay. Then we say that lambda is in the resolvent set of A. Okay, so this is notation rho A. So this is the resolvent set. Okay. So we also denote this only resolvent. Okay, so resolvent so R lambda A is lambda I minus A inverse. Of course, this is defined for lambda in rho A. The complement of rho A in C, the complement C minus rho A, this we denote it by sigma, is the spectrum. So, in case of bounded operators, okay, so bounded operators A. So, we know that sigma A is non-empty and compact. Okay. So rho A is the resolvent is large. Because it is the complement of a compact set. Okay. So, essentially the Hill-Yoshida theorem requires that the resolvent has to be large enough. Okay. That will make it precise. Okay. But in case of unbounded operators, the situation is different. It may happen that sigma A empty or sigma A. Okay. So, that is that is the difference. Okay. So, of course, we do not want such a situation. So, for many of our differential operators, we have some satisfactory non-empty sets. But however, what is true is, of course, this definition we are not using any in the definition of spectrum and resolvent, we are not assuming A is just linear. Okay. So, just a word about this thing. Okay. So, we have to just because of this, in general the product of two linear operators has to be properly defined. So, let me just make that okay. So, suppose lambda belongs to the resolvent set. Okay. So, we know that this lambda I minus A inverse exists. So, its domain is whole of X, okay, but the domain of lambda I minus A. So, we have lambda I minus A, lambda I minus A inverse X is equal to X for all X in X, because this domain is whole of X. Whereas, if you reverse the order, and this is valid only for X in dA, because this makes sense only for X in dA. So, combining these two, we can write this as lambda I minus A inverse lambda I minus A is restriction of the identity, which is equal to lambda I minus A. So, these are simple observations, but one should keep these things in mind while doing computation. Okay. Next, okay. So, what is important is, so in the case of bounded operators, we already know that sigma A is compact. So, rho A is open because it is complement of the. Okay. So, in general we have this. So, rho A is open, it could be empty, but rho A is an open subset, and hence the sigma A is closed. This we have even in a general for unbounded operators. Okay. Again, a simple property to check. Okay. So, the importance of rho A being non-empty. Okay. So, if rho A is non-empty, then A is closed. So, it is a very simple exercise, you should do that. Okay. Okay. So, one of the important properties of this resolvent, this lambda A. Okay. Though this is very similar to the case of bounded operators. Okay. So, this so let me just quickly state that. Okay, this so simple properties. So, this you should verify, you should just sit down and do this work, it is not very hard. So, this is resolvent identity. So, R lambda A, it is so simple, but very useful. Okay. Where is that? Mu minus lambda R lambda A. So, for lambda mu belonging to rho A. So, this mapping, the mapping of course, when the rho A is non-empty, okay, otherwise this lambda going to R lambda A is an analytic mapping from rho A to Bx. Okay, so this itself is a Banach space. So this is an analytic mapping, and okay, so this we have this expression. So let me just write that d n by d lambda n R lambda A is n factorial R lambda A, very similar to the scalar function case. So, n equal to these expressions are used in the proof of Hill-Yoshida theorem, but we are not going to those details, but they are certainly useful in obtaining estimates for the resolvent. In fact, Hill-Yoshida theorem, the conditions are essentially on this resolvent, on the estimate of this R lambda A. Okay. So, that is fine. So, I just maybe just one simple example just for you to work out. Okay. So, this is the discrete case. I just so one example, let me just state in the. So, in this example, this is I take little L2. So, these are all space of sequences which are square summable. Okay. So, and let A equal to A n be any sequence, need not be in X. Okay. Sequence of either real numbers or complex numbers, so it does not matter. So, define the operator A by A x. So, I take a sequence in the space L2. So, I want to know what is its nth coordinate. So, this is simply A n x n, n equal to 1, 2, etc. So, this is the definition. So, I want this obviously A x again back to be in A L. Okay. So, this dA so this set of all x in X such that this new sequence A x. Okay. So, this I simply write as A n x n again in L2. Okay. So, then only this makes sense. So, then A is from dA to L2. Okay. So, here is properties of A. So, very easy to verify, but work out all these things. So, this is the proposition. So, 1 A is a densely defined closed operator. The spectrum of A, okay, is precisely you take all these A n's from the sequence and then you take the closure in C. A is bounded if and only if A is a bounded sequence. Okay, just one more thing, just there are many more, but just let me. So, suppose real part of A n is less than or equal to some omega 0 for all n. Okay. So, if A is a real sequence, then it is just bounded above. Okay. So, there is no absolute value here. So, it is only bounded above. Then any lambda bigger than omega 0 is in rho A. Okay. Work out this interesting, and this is an example of a multiplication operator. We also see the continuous analog when we study semi groups in function spaces. Okay. Though it looks easy, but they are not. So, you have to really work hard, and so many details are missing. So, you have to fill them. Refer to some good books on functional analysis and work out. So, I will stop here and we will continue next time. Thank you.